working at the DFKI, which is the German Research Center for Artificial Intelligence. And we will talk about 3D transformation in Python. And I think Alexander will have some example robotics taken from the robotics field. And one information is that sometimes you will have some animations. And for epileptic people, Alexander will warn you before these animations.
Yeah, so the warning, I have some animations, there's some flickering, so if you have problems with that. Yeah, I'm talking about transformation in 3 dimensions. My field is robotics, so I'm working in the Robotics Information Center of the DFKI. And I'm a computer scientist, and I was always confused by 3D transformations, so I really wanted to understand how to use them, in which case, and as a computer scientist, my natural behavior is then to write a library about that, and I think it could be useful for some people. So I wanted to also talk a bit about that and about the challenges when you deal with spatial data in robotics specifically. So why did I write this library? There are a lot of different conventions out there to represent 3D transformations, and also different conventions, different representations. It's just confusing in the end. And sometimes you just quickly want to visualize some things. And that's also done by the library. But let's start with the basics. So there are some basic terms that I have to explain here. You probably all know what a position is in 3D space. It's characterized by 3 numbers. An orientation is a bit more complex. It's characterized by 3 orthogonal vectors. So these are these 3 arrows here. And if you combine both, is what you get is a pose. And now for the orientation, you usually use a rotation matrix, a 3x3 matrix to represent it. For a pose, it's a bit more complicated. So you have a 4x4 matrix, which includes the rotation matrix and the 3 numbers that give you the position. And there's also another interpretation of that. For the 3 real numbers, you can also see it as a translation with a linear displacement along parallel lines. An orientation or rotation matrix could also represent a rotation, which is a circular displacement about some fixed point. And if you combine both, you get a rigid transformation. Again, you use the same representation, also transformation matrix here. So it could be a bit confusing. Another basic term that I have to introduce is so-called coordinate reference frame. And that's defined by a position and orientation. And it's usually attached to a rigid body. And we can illustrate it like that. You see here that we use 3 arrows. So the red arrow for the x-axis, the green arrow for the y-axis, and blue for the z-axis. And in the real world, things get a bit more complicated. So what you usually have is not just one transformation, but you have graphs of transformations. So example for that is, for example, the kinematic structure of a robot. And for that, you can use, for example, such a tool like the Transform Manager from PyTransform PD to manage these. So what you do here is you represent your nodes, or the nodes represent frames, and the connections between the nodes, the edges are transformations. And then you can use this library, for example, to add transformations like that. So you say there's a transformation between the end effector and the robot, and that's basically a 4x4 NumPy array, which is the transformation matrix. And then you add also transformation from the object to the camera and from the camera to the robot. And then you can do some more interesting stuff. You can request transformations that are previously unknown because you can follow this path here. So you want to request the transformation between the end effector and the object. And for that, you can just request it from the Transform Manager, and we'll compute this path basically, and following along the path, it will invert and concatenate transformations as needed. So that's a quite nice tool. So in reality, things get a bit more complicated. So this is an example of a graph of a simple robotic hand. For robots, we often use the so-called universal robot description format to describe the mechanisms. And you can simply import them or read them from a file here, and then you can produce such a graph easily with PyTransform PD. Then how do you use that actually? So here's an application that I've been working on in the past 2 years. So this is a transfer of a motion from a human to a robotic hand. So what we have here is the right top. You see the mesh of the hand. So this has been already reconstructed from a motion capture system. And that's why you also see these spheres here that actually represent markers of the motion capture system. And you can also measure, for example, the pose of an object that we try to grasp with the hand. So here's an animation. And then we try to transfer the motion in each frame to the robotic hand. And for that, you have to solve some complex optimization problem. For each of the fingers, you try to minimize the distance between the positions with comparison to the human hand. So by changing the joint angles, and you have to compute these transformations along the path each time in each frame, and even for each iteration of the optimizer. When you've done that, you can also collect a larger data set. Like for example, here we have about 200 grasps of a pillow, and I just try to show here the trajectories of the hand without the fingers, just the position and orientation. If you want to know more about it and how the transformator can be used here, you can have a look at the GitHub repository. Now, how do we actually use the data? And here's another application that I wanted to introduce, and also to highlight a bit the problems that you have to deal with when you work with 3D orientations. So to simplify the problem a bit, here we only have one trajectory, and we want to use imitation learning, so some form of machine learning. And the problem here is you have given one or more solutions to some specific problem. We then have to find out how do we actually represent it such that we can actually apply machine learning to it. More specifically, often the orientation is a problem here. So it's complicated. There are many different representations for orientations or rotations. The most commonly used one is a so-called rotation matrix, which is a 3x3 matrix, which has 6 constraints. You also have things like quaternion, which is a 4D vector, or minimal representations that only have 3 real numbers. But all of them have drawbacks and pros. So some of the most common problems are in the rotation matrix, as I said before, has 6 constraints. So when we want to apply machine learning, it's not easy to enforce those constraints. When you have minimal representation, you often have discontinuities and singularities, which is also not good for machine learning. And quaternions have the problem that they are elements of 4-dimensional unit sphere, but they have a double cover. That means the quaternion Q is the same as minus Q, which is also not so good for machine learning. But at least one guy tried to say that it's a good idea to use quaternions, and it actually is, because you can also easily normalize unit quaternions just by dividing a unit quaternion by the norm of it, and then you can generate a valid orientation, and that's also something you can easily do when you want to apply machine learning. So how do you fix this double cover problem? You first have to pre-process your data. And there's an easy way to do that with PyTransform 2D. You just call this function, smooth quaternion trajectory, and then you can also use machine learning. There are more pitfalls here. I just wanted to quickly highlight them because it's really complicated sometimes and really confusing. There are actually 2 different conventions how you do quaternion multiplication, the Hamilton convention and the JPL convention, and you should always use the Hamilton convention. There's a paper about that if you want to know more about it. Another really confusing thing is that when you deal with data sets that contain quaternions, there are 2 different ways to organize those 4 numbers. So you have a scalar part in quaternion and a 3-dimensional vector part. And it's not really always so clear what the scalar part and what the vector part is. Sometimes it's the first part, it's the scalar part, sometimes it's the last part. And I usually recommend to use it at the first part, but it's really there's no real convention out there. So it's complicated. So completely different topic now, but if you want to generate these kind of illustrations or visualizations that I just showed you, it was also quite complicated for me before I wrote this library. And I just wanted to quickly show you that actually with PyTransform 3D, it's now easy to use the Open3D visualizer to do these kind of visualizations. And you can call it with a matplotlib-like interface, so you can create a figure, you can plot a transformation, plot a graph of transformations that might also include collision objects, and so on. And in the end, you just call show. Also, another feature that I wanted to show you here that is quite interesting is you can also use PyTransform 3D to deal with uncertain transformations, and that's also a quite complicated topic again. So let's assume you have a rover that's going forward and it has wheels, and usually also these wheels slip a bit. So you have some uncertainty in the rotation about the z-axis usually in each step when you apply a certain velocity. And when you go forward for 100 steps, you can do Monte Carlo simulation like that, and you get these kind of trajectories here, and you can measure the final position. Then you can estimate a Gaussian about the positions, but you can see that it doesn't really cover that distribution well. So what an actually theoretically sound approach to that is the so-called banana distribution, which you get when you work in the space of exponential coordinates of transformation. And to show you what that is, first, again, it's confusing, so there are many different representations. Usually we use transformation matrices to represent poses, but for this application, we'll go more into the direction of exponential coordinates, which is a more convenient representation in this case. Exponential coordinates are 6-dimensional vectors, and I'll quickly give you a short introduction to screw theory here. So the basic idea is a mechanical screw. When you turn it, this results in a translation and a rotation at the same time. So how do we frame it mathematically? Well, first we have to define a so-called screw axis, which is defined by some point on the axis q and some direction vector as hat. And we also define a so-called pitch, which is the relation between translation and rotation. And then we can write it down as a 6-dimensional vector. This is the axis. We multiply it by the angle about which we rotate it. And then we get a 6-dimensional vector, which are the exponential coordinates. You can map that 6-dimensional vector to a transformation matrix with a so-called exponential map. And you can also do that with PyTransform 3D easily with one function call, but that's not really so interesting for us at the moment. So we want to solve this uncertainty propagation problem. And for that, you can define your pose that you currently have as a transformation matrix. You have to define the covariance of this pose as a 6x6 matrix in exponential coordinate space. And then you also define your velocity as a transformation and also 6x6 covariance matrix of it. And then in each step, you concatenate the velocity with the estimated pose. And in the end, what you get is this banana distribution in our example. And again, we say that we represent the pose with the transformation matrix, but the uncertainty is defined in a 6-dimensional space. And then we project the ellipsoid representing this distribution back to 3 dimensions. And what we get is this kind of banana distribution. We can also do that for robot kinematics. As you can see here, we get this nice umbrella of potential positions of the end effector. Now I conclude with mentioning that this has been funded partially by the European Commission through the April project, and I'm open for questions now.
Thank you, Alexander, for the presentation of the features of PyTransform 3D. So do we have some questions? I think we have 5 minutes for questions. Yes.
Thank you for the super interesting presentation. So I wanted to ask about when it comes to machine learning models with time series. Typically, we would then, if it would be position or displacement, we might sometimes want to aggregate and take, I don't know, the average over a window. When it comes to quaternions, though, that becomes a bit more difficult and you need to use Slurp. But then would you suggest to use directly the quaternion or convert it into a different representation, like hopefully not Euler angles, something else, or axial angles, helical, or something like that?
Yeah, not Euler angles. Please don't use Euler angles. It's just for user interfaces, it's nice, but usually not for averaging. So there's a solution. I think it's not implemented currently for orientations, but for transformations. And again, it's in this exponential coordinate space. So there's also an exponential coordinate space for orientations. And that's the rotation vector representation. But you cannot just average those rotation vectors. You have to perform some kind of optimization. That's currently implemented in this library for 6-dimensional pose representation, so for the exponential coordinate, but it's currently not implemented for the orientation. So that's, I mean, I'm also interested in contributions. So if you're interested, I think it shouldn't be too hard to convert to apply that also to orientations. But basically, you can also just use the exponential coordinates of transformation and then just leave the positions at 0, and you can apply this approach. So that's also included in the library.
Sounds good. Thanks a lot.
Any more questions? Well, maybe I have one. What are you planning for the future of PyTransform 3D? What are you dreaming about?
Yeah, so I want to avoid that it grows too big because it's just a simple tool and library. So one aspect would be to reduce a bit the dependencies, and then I think it's in the end is a tool to for representation conversions, for visualization, and just to simplify the workflow a bit. So whatever goes in this direction, I think would be a good new feature for the library.
Okay, thank you. Any question? Okay, thank you very much, Alexander. And now we have a half an hour break. Thank you again. Big applause.